The trigonometric ratios of 5 angle measurements are important for every student to know, memorize, and understand. Those angles are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. They're also referred to as the special angle measurements. Now, for the purpose of this video, we are not going to be looking at the 0 degrees or 90 degrees. We'll just focus on 30, 45, and 60. The reason for that is because our study of trigonometry right now is based on right triangles, and your angle measurements are going to represent the acute angle measures that you have in a right triangle. And you can't have acute angle measurements of 0 degrees or 90 degrees. It just wouldn't make sense. Right, you take a look at the picture that I have here. This is actually an isosceles right triangle. But if you've got 90 degrees here, you can't have 90 or 0 in one of those two spots. Okay, so we'll address those a little bit later when we talk about trigonometry not directly attached to right triangles. In example number 1, we're going to take a look at the 45-degree angle measurement, and we're going to figure out what the sine of 45, the cosine of 45, and the tangent of 45 would be. Now, recall from geometry that an isosceles right triangle is a right triangle where the leg lengths are the same. So you're going to see this is my right triangle. These are the leg lengths, which I'll be referring to as x for this one, because it doesn't really matter what actual numbers they are, except that they are the same as each other. All right, now this is an isosceles right triangle because these two sides are congruent. So that would be the base. Typically, an isosceles right triangle would be positioned like this. That means that your right angle is the vertex, but we're going to be looking at it from this perspective. All right, this is also called the 45, 45, 90, because if these two sides are the same, then these two angles are going to end up being the same as well, which means that if you took 90 from the 180 and then divided the remaining 90 of your 180 between these two, then you're going to get 45. You can also look at this as half of a square, and that diagonal would break the square, so you get 45 and 45. So lots of different ways you can look at that and confirm it. All right, so our job here is to figure out what would be the sine of 45, the cosine of 45, and tangent of 45. And when we do this, we're going to actually solve for these in their exact form. That's what's going to be important about them. See, I can take a calculator. And, of course, if I'm set for degrees here, I can just type in the sine of 45. Okay, I can do that. But it ends up that number can be presented very nicely as a fraction or as a ratio. Okay, it can be represented very nicely, whereas this is going to, so if you're going to use this, you're going to have to round it at some point. So that's what we want to get past is having to use those decimals. And we have these special angles that we can do this stuff with. So this will be one of them. All right, what I'm going to do, let's think about the definitions first. Like suppose I want to know what the sine of 45 is. I'm going to do all of them. But suppose I want to know the sine of 45. To do that, I would have to figure out the opposite and the hypotenuse. I would need to know those two things so then I could set up that ratio. Now in my picture, let's let this be the theta just for a reference point. Now it really doesn't matter in this case which one's theta because they're both 45 degrees, but just for the sake of reference, I'll put it here. What we know from my picture is that the x is the opposite side and the x is the adjacent side. But what we don't know is the hypotenuse. We don't have any way of describing that one. Okay, that does mean, though, we can answer one question. We can figure out, not sure where I want to write it, I'll just put it over here. The tangent of 45 is pretty straightforward. The tangent of 45 is the opposite over the adjacent. So if I take x and I divide it by x, well, what's x divided by x? It's 1. Okay, the tangent of 45 is actually equal to 1. Let's check that one out. The tangent of 45 is 1. Okay, so that one's easy. That's an easy one there. The sine and the cosine, for those, we have to have the hypotenuse. So what I'm going to do is a little bit of Pythagorean theorem here. Let's do a different color so it doesn't get all mixed up. With Pythagorean theorem, I'm going to take the leg lengths. I'm going to add those together. I'm going to square them down together. So I'm doing Pythagorean theorem here. Going to square them. I'm going to add them together. Set that equal to the hypotenuse squared. don't have a letter for the hypotenuse squared, let's just go ahead and call it h. That'd be fine. Okay, so x squared plus x squared is going to be equal to h squared. These are actually like terms. These are like terms, so if I want, I can go ahead and add them together, and I'm going to get 2x squared. That would be equal to h squared. And if I want to solve for h, because that's really what I'm doing here, is I want to know how to describe h. If I want to solve for h, I'm going to need to undo the squaring, which means that I'm going to square root. So I'm going to take the square root of both sides. That'll give me h. Now, how do I actually deal with this? Well, if you have things that are being multiplied together, you can sort of separate them within the radical and take the square roots where it's possible. Like, it's possible to take the square root of x squared, but it isn't possible to take the square root of 2. So I'm going to go ahead and square root the x squared, which is x. And that part is allowed to move on to the outside. So I get an x times the square root of 2. And that's what h is equal to. See, I can take the square root of x squared, which will give me an x, and that is allowed to move outside the radical. But since I can't take the square root of 2, that's going to stay inside, and we get this. That's what it looks like. Now, I hope that you remember, at least from geometry, that you had done something with special right triangles. And one of them was the 45, 45, 90, also called the isosceles right triangle. And this is actually just the shortcut that would help you figure out that side. So in this type of a triangle, if you had leg length, you can actually just multiply it by the square root of 2, and that's going to give you the length of your hypotenuse. Or if you have the hypotenuse, you can divide by the square root of 2, and it'll give you the leg lengths. Of course, that is only when you have the isosceles right triangle. Okay, but now that I have a description for the hypotenuse, I can go and revisit the sine of 45. The sine of 45 would have to be equal to the side opposite of it, which would be x, divided by the hypotenuse, which looks like that. All right, now, the x's are going to cancel, which is something that you also saw here with the tangent and the way the x's cancel. So that confirms the idea that we don't really need to know what the side lengths are for this, that I could actually just use x's, and as long as the two sides are the same, then the results I'm going to learn from this will not matter. Okay, so we get to see the x's cancel again. That means that we have 1 over the square root of 2. Now, we also have a rule in mathematics that says we can't have radicals in the denominator. You can't have that square root 2 in the bottom. So the easy fix to that is to multiply the bottom and the top by the square root of 2. Because if you multiply the square root of 2 by the square root of 2, you actually just get 2. Remember that a square root is the square root of a number is the number that when multiplied by itself gives you the number inside. So if I actually multiply it by itself, square root 2 times square root 2, the radical will drop and I'll just get the 2. Now for the top, 1 times square root 2 is square root 2. Okay. And let's check that out, because a little earlier, I had typed in the sine of 45, and I got that weird number. Now my claim here is that the sine of 45 is also the square root of 2 divided by 2. So, make sure I get outside of that radical. Whoops, divided by. The square root of 2 divided by 2 is exactly the same thing that we have there. So what we're going to be doing in class is not using the decimal form, but using this fractional form, which looks better here when they're actually vertical to each other. We're going to be using that as the sine of 45. Now, cosine. We shouldn't need to write too much for this one. Actually, let me recap the things that I know. I know that the sine of 45 is going to be square root 2 over 2. We have not figured out the cosine of 45. It's going to be pretty easy though. And we know that the tangent of 45 is 1. So we've got those two figured out. All right, cosine of 45. The cosine of 45 is going to be the adjacent divided by the hypotenuse. All right, let's take a look here. The adjacent is the same thing as the opposite. So how much different is the adjacent over the hypotenuse going to be than the opposite over the hypotenuse? They're going to be the same thing. So the cosine of 45 is also the square root of 2 over 2, and we will verify that with the calculator. There it is. Next, what we're going to do is take a look at the 30 and 60 degree angle measurements. The neat thing here is that the 30 and the 60 degree measurements actually work together in a right triangle, right? If you have a right triangle and one of the angles is 90 degrees, the other two have to be complements of each other, and 30 and 60 happen to be complements. So we're going to be able to take care of two of them at once here. You might recall from geometry the 30, 60, 90 triangle and that it had some shortcuts in it. What we're going to do here at the beginning is redevelop those shortcuts just to make sure you know them, and then once we have those shortcuts, it's going to be easier to evaluate the sine and cosine of and tangent of those angle measurements. So it all begins with an observation that a 30, 60, 90 triangle is actually half of an equilateral triangle. So I have here a picture of an equilateral triangle. That means that all the sides are equal. It also means that all the angles are equal. So if I take 180 degrees divided between three angles, you're going to get 60. 60, 60, 60. Okay, so this angle is 60 degrees there. Now my focus is going to be over here because we want to talk about the 30, 60, 90. But yeah, there is an equilateral triangle and all the angles would be 60. Now, if you cut it in half, of course, the shape is symmetric. I'm assuming everybody will accept that idea that the equilateral triangle is symmetric. And if you fold it in half, you're going to create a perpendicular here. So that'll be 90 degrees. And you're also going to break apart the 60 degrees that was up at the top. You're going to split that in half and get 30 degrees. So that would be your 30, 60, 90 triangle. Now, what we want to figure out is how do the sides compare to each other so that then we can take those and apply it to the trig ratios. Okay, so we're going to let this length right here be a 2x, which might seem a little bit odd because usually we just introduce a variable like x, but it's going to work out mathematically a little bit better if we let that be a 2x. All right, now what do the other two sides end up looking like? Okay, so this is 2x, which would mean in the equilateral triangle that that's 2x and that the base is 2x. But this is only half of the equilateral triangle. So if the whole thing here is 2x, that means that this short leg is actually just x. And that is the reason why we choose 2x to represent this first. If that's 2x, it's easy to cut it in half and just call that one x. Now, for the third, there isn't any really just like super quick way of saying what that one would be. But we do have two of them that compare correctly, and we could use those to do some Pythagorean theorem. So I'm going to take, okay, this will be a little bit tricky because this is a leg and that's a leg. Okay, so I'm going to take x squared plus, for right now, let's just call that b. Okay, just call it b, so we have a filler there. Okay, so if I took x squared plus b squared, that's going to be equal to the hypotenuse squared, which is 2x squared. Notice that I did put that in parentheses because in a moment I'm going to have to square that, and when I square it, it's important that the whole thing gets squared. Now, I guess that's actually what I'm doing right now because there isn't really anything else to do here except copy it down. Okay, so 2x squared is 2x times 2x. 2x times 2x. So the 2 times 2 is going to give you a 4, then the x times x is going to give you an x squared. Now our goal here is to figure out what is b. So I'm going to move this x squared over to there, do that through subtraction. So b squared is going to be equal to 3x squared. I'll then take the square root to get that down to just b. And that means I'm taking the square root of 3x squared. Now, as mentioned in the other problem, example number 1, you can take the square root of anything that you actually can and then move that number outside and leave things alone, leave things inside that you can't. So the x squared, you can square root that and just get an x. So that's going to move outside the radical, but you can't take the square root of a 3, at least not nicely, so we're going to leave that one inside. So that is the length of the third side. Go ahead and erase that. This will be x root 3. So the way the shortcut works is if you did have a 30, 60, 90, right, you're only looking at that side here. The hypotenuse is going to be twice the length of the short leg, and the long leg is going to be the short leg multiplied by the square root of 3. That's the comparisons that we have here. For example number 3, what we want to do is take the comparisons that we just saw with the 30, 60, 90 shortcuts and use that to figure out what the sine of 30, sine of 60, cosine 30, and so on, what all those would be in their exact form. Okay, so we'll go ahead and just start with the sine of 30. All right, the sine of 30 is going to be equal to the opposite divided by the hypotenuse with respect to where the 30 degrees is. So that means that my theta is up here at 30 degrees. So the opposite of that is x. The hypotenuse is 2x. So the sine of 30 is going to be x over 2x, which the x's will cancel and evaluates as 1/2. So that one actually turns out to be a really nice one. Sort of like the tangent of 45. All right, so if I take the sine of 30, you can see that we actually do get 0.5, which is 1/2. All right, so let's take a look at sine of 60. All right, the sine of 60 is also going to be the opposite divided by the hypotenuse. So the hypotenuse is still the 2x, but opposite of the 60 degrees is now going to be x root 3. Okay, now the x's are going to cancel again. X's cancel, and you are left with the square root of 3 over 2. Okay, let's verify that in the calculator. The sine of 60 comes back as that number. And by the way, you might want to start recognizing these numbers, because when you see this show up in a calculation, it tells you what angle you might be looking at or what the ratio should be. So these are good to start remembering. But the comparison is to type that in and see that it's the same thing. So again, you might want to memorize that, start the process of memorizing that when you see 0.866, that represents the square root of 3 divided by 2. You'll see that more times than you could count. All right, next we're going to do the cosine. Cosine of 30. All right, that means we're going to go look at 30 degrees. The definition of cosine is the adjacent divided by the hypotenuse. Okay, the adjacent to the 30 is going to be x root 3. And the hypotenuse is 2x. Now that one should look pretty familiar because it's the same thing as the sine of 60. That is true there. And you get square root 3 over 2. And I'll go ahead and type that one in just so we can see this is all working. So now cosine of 30 should be the same answer that we're seeing there. Yeah, they are the same. And then we already did sine. Then for cosine 60, you might be able to predict what that one's going to be. The cosine of 60, here's your theta. It's going to be the adjacent x divided by the hypotenuse. So we're going to get x over 2x. The x's are going to cancel, and you get 1/2. The cosine of 60 is actually 1/2. That's 0.5. There you go. All right, now I'm going to give you a little bit of piece of information that you're going to see later on, but you might remember it or might plant a seed in your brain for it for later on. Between sine and cosine, if you use complements, like the sine of 30, the cosine is 60, so 30 and 60 are complements of each other. If you use the complements in the two different functions, you do get the same result from there. So we could do the same thing with like sine 20 and cosine 70. Those will give the same answers, or sine 70 and cosine 20 will actually give the same answer. Now that's actually a totally different lesson. You don't need to know that today, but we're actually seeing it happen here, which means that I should probably at least identify that it is there. All right, now the tangent of 30. All right, so tangent is the opposite over the adjacent. So I'm gonna slide this down. All right, this is our theta. It's gonna be 30 degrees, and we need the opposite of that, which is x, divided by the adjacent. So this is x over root 3. Actually, that's x over x root 3. I don't think I said that right. The x's are gonna cancel. You're gonna get 1 over the square root of 3. And we don't like having radicals on the bottom, so we're gonna multiply the bottom by the square root of 3, the top by the square root of 3, which is gonna change that denominator into a normal 3, which is what we want. And the top is going to be the square root of 3. So that is the tangent of 30. Let's go check that one out. All right, tangent 30 is that number 5, or it's 0.577 at the beginning, and my claim here is that it is the square root of 3 divided by 3, square root of 3 divided by 3, and there it is, same thing. All right, the last one is the tangent of 60. All right, when you switch perspectives of your theta, when you switch from the 30 to the 60, you're still using the same definition, which is opposite over adjacent. But because when you switch over to the 60 degrees, these just switch roles. Now that's the opposite, that's the adjacent. So you're really just gonna have the reciprocal of what we saw here, which is x root 3 over x. These cancel, which means that you get the square root of 3. So the tangent of 60 is actually just the square root of 3. And we will test that out. We got that, and the square root of 3. You should already, I don't know how to type that in. You should already know that that's approximate, that 1.73 is approximately the square root of 3. That was back from geometry, but there it are. They are all verified.
Later, blah.